All right, everybody, we have not yet talked about redox in organic chemistry. So what I'm going to do is summarize things for you here. You'll see on many videos, it tells you why we have to do a slight tweaking, modification of our definition of oxidation and reduction, because carbon never loses or gains electrons. So we talk about electrons moving away from or towards carbon. And basically, it's not letting me type here. In organic chemistry, redox is done on a bond. In organic chemistry, redox is done on a bond by bond basis. I was hoping it would have typed that for me, and it did. Norco, interesting. Okay, I'm gonna just type.
Norco and one's looking at Norco.
Yeah, I was thinking Narcan in my brain for some reason. I don't know why. Yeah. Redox in organic chemistry is done on a bond by bond basis for each atom in a molecule. If an atom has 4 bonds, each one is assigned an oxidation state according to the following. 1, +1 for a bond to a more electronegative element. This is important. We gotta make it important. All right. 24. There we go. And move that over. Don't worry, we're not done with this sentence yet. Redox and organic is done on a bond by bond basis for each atom in a molecule. If an atom has 4 bonds, each one is assigned an oxidation state according to the following. Yeah, I shouldn't even have to say that. Each bond, hello, bond, is assigned an oxidation state according to the following. +1 for a bond or more electronegative atom. Wow, I don't like that. It's not as nice as Word. 2, -1 for a bond to what kind of atom? Yes. And what do you think if the electronegativity is the same? 0 +0. How about -0? Just kidding. For a bond to the same electronegativity element, the 2. For a bond to an element with the same electronegativity would be the proper English, right? An element with the same electronegativity. Save. All right, so we're going to be doing this. We're going to draw some Lewis structures. We're supposed to draw a Lewis structure for species 1. There's a pattern in there on the left. It says CHO if you read it from right to left. How do you draw that pattern? And what functional group is that pattern? Thank you. Aldehyde. Carbonyl. H. It says Lewis, so I guess we have to show all the atoms, right? And then a C, C, H. And I'm not done, I know that. But I'm just translating, that's atom number 1 and that's atom number 2. How do I finish the octets for the second and third carbons here?
We added them.
Okay, we add a pi bond. And it's not quite done, is it?
Yeah, no.
Another pi bond. Yes. Okay. And that is the answer there. And I'm going to copy paste if I'm lucky. I don't think I'm lucky. What's the best way out of this situation? Move that. Copy. Paste. Not move it. Move. My apologies. Eliminate. Control X. I know, it looks like a disaster just happened, right? This is all because I wanted a copy of that. And then we got this guy moving back upstairs. And it's going to cover stuff. This is going to be a disaster. Watch this. Dr. Whitaker's made this mistake before. My molecule is now covered. I think I made a copy, huh? Love you too. I could have this thing drawn 3 extra times by now, right? Okay, I'm going to do these sentences now. For carbon, for CI, you got in black. What do you get for a bond to a less electronegative H? It says in the sentences, people, -1. What do you get for a bond to a more electronegative O? +1. These numbers, I just want to be very clear, are ox states. What's that stand for? Oxidation states, not formal charges. That's why I'm doing them outside my box. I don't want you confused thinking there's formal charges in my molecule. What about the other bond to oxygen? It says for each bond is assigned. It doesn't say what kind of bond. It says each bond. Same story for this second bond. What about the fourth bond from carbon to carbon with the same electronegativity? 0. Add them up, please. -1, +1, +1. Answer equals. Hello?
1.
Yes. Answer for atom 1 is +1. Here it goes. You ready? Here it goes. Yes, sir. Where do you get that answer from? I think it's clear where I got it from. Atom 2. We'll do in purple. CII. What do you get for a bond from a carbon to a carbon every time? 0. What about for a carbon to a carbon? That's the same question 4 times, isn't it? I'm just going to put 4 zeros down. 1 for that bond, 1 for the middle pi, and 1 for the top pi. 4 zeros. I just wanted to be very clear. You better take 4 numbers so you got 4 bonds. Each bond has a 0 oxidation state because each bond is between 2 atoms with the same electronegativity. Which one did I have? 0? No, that was from this carbon's perspective. To answer the question, the oxidation state of CI, I only need to talk about the 4 bonds that CI has. New question, what's the oxidation state of C that's II? This bond, 0. This bond, 0. This is all from this carbon's perspective. Okay? And you're going to get a big fat 0 there, 4 zeros. I wrote +4. Isn't that great? That is fantastic. Yeah, 0. Big fat 0. That was the new math that is all the rage now. 0. 0. There you go. Looks like a Q on a corner. There we go. 3. Species 2 goes here. Somebody's done species 2 already. Wow, you guys are fast. There's 2 methyls, and ladies and gentlemen, it's a Lewis structure. You have to show. No, I'm going to be smart in my older age here. I'm going to draw it down here. It's an isopropanol. It's going to be C with 3 H's. I will be moving it into the box. Oops. I totally messed up, by the way. There's the 2 CH3s. They're attached to a C with 1 H. It has an O bonded to H. That ain't fitting in my box, is it? And in terms of numbers, the carbon with the OH is III. Please. Clock. Group. Shrink. Shrink. Didn't shrink enough. There we go. Let's do the 4 numbers down here. You get 0s for bonds to C. You get a -1 for a bond to H. How come? Because H is less electronegative, a little bit. H is less electronegative than C. We're doing C, Roman numeral, or III. And what about bond to a more electronegative O? It's another 0, isn't it? Yeah. Oh, this is a tricky little question because it didn't ask you to draw species 3 and 4, but you really kind of have to. We'll do those in orange.
Just instead of the double bond, it has 2 H's.
I think you're right. There's the bond for species 3 is drawn right there. I wasn't asked for a Lewis structure, so I don't need lone pairs. Lone pairs don't affect oxidation state. I hope you got that message. It's only bonds. And we got IV up here. It's a pretty natural oxygen. Each atom bonded to that O is less electronegative, correct? So what do you get for oxygen? -2. I'm just not showing my work. You don't have to show the work. What about V is the carbon next door. It's got 2 bonds to less electronegative H, that's -2. 1 bond to a more electronegative O, that's +1. So I'm at -1 and a 0, right? Oh my goodness, I'm making you work for your money. Not a Lewis structure, but it has enough info here. That's VI. Each of the 2 bonds to oxygen gives a +1, right? Why? Because oxygen's more electronegative. +1, +1, 0, 0. +2. VI. +1, +1 for each of the H's. 0, 0 for each of the bonds to C. And then you ask yourself, hey, species 2 created species 4. I hope you can see that. Species 2, all the carbons in species 2 became all the carbons in species 4. How do you know it's not species 2 became species 3? There's several clues. Give me one of them. Yeah, the dimethyl is the big giveaway, right? Parts in the molecule that didn't change are what's the giveaway. You could say the C triple bond to C with an H at the end didn't change either, right? Okay.
Why is IV for O -2?
IV for O is -2 because each of the bonds is to a less electronegative atom. 2.1 and 2.5 versus 3.5. 2.1, 2.5, 3.5.
So from oxygen to carbon, it would be -1, but from carbon to oxygen, it'd be +1.
From the carbon's perspective, that bond is +1. From the oxygen's perspective, it's -1. We only look at one atom at a time. So do we agree that atom I is becoming atom IV? Atom I is the same oxygen as oxygen IV, right?
Just more hydrogen.
Yeah, I mean, but it's the same oxygen. So whatever happened to 1 becoming 4 is either oxidation or reduction if the number changed, right? And the oxidation state went down. It became more negative. Okay? How do you get more negative? Do you gain electrons or lose electrons? You gain electrons. Now you can say GR. With oxidation states, you can go back to your old memory tricks. Gaining of electrons is reduction. Okay, once you've got proper oxidation states, you can go back to that. Please verify to yourself that you know none of the carbons in this molecule gained electrons. This carbon here is surrounded by 8 electrons. In the product, the same carbon is surrounded by 8 electrons. 2, 4, 6, 8, 4 bonds, right? Carbon's never losing or gaining electrons in reality. It's just in this reaction, the electrons got closer to carbon. What do you call that? Somebody said it already. Reduction or oxidation? Reduction. So looking pictorially, this blue species became this orange species. The electrons around this carbon were predominantly close to oxygen, right? When you're done, they're much closer to carbon because you got rid of one of the bonds to O and replaced it with a bond to a less electronegative H. You moved the electrons closer. Moving electrons closer is reduction, like gaining. We had a question. Oh, did I shift everything? Yeah, I didn't label it right here, did I? Thank you for catching that. That would have been very misleading. I don't have to erase that. I have to erase this, right? I just didn't follow my own labeling. Get rid of 1 and whatever we thought was 3. Was that a 3 there or 2? That's a 2. Start over. Had the labels wrong down here. 2. Gonna fix them. This was II, right? CII. And there's I. So start over for I for me. We haven't done I at all. What does oxygen feel in a bond to carbon, a less electronegative carbon? -1. I'm going to do it in red. And same thing for the other bond, right? This is oxygen. OI equals -2. No, it wasn't I becoming that. So, oh, yeah. This did not work out as well as I thought, everybody. And 2, we did all the work and then I erased it. 2 was all the numbers are in black. You got a +1, correct? And that is the real Roman numeral 2 label was on a carbon, not an oxygen. So that is +1 for CII. And that yellow arrow should be pointing to that. Right? Because this was for CII. There's the answer, and there's where it came from. And in terms of carbon, it's 2 becoming 5, right? And 1 became 4. That was correct. But it wasn't, the word was not correct. Tell me why the word is incorrect up there. I'm getting my label back, trying to get the color back. Going from -2 to -2 is not reduction. If your oxidation state does not change, you say. What do you say? You say nothing. Thank you. Good answer. Don't say anything. But carbon used to be 2. At the end here, it's 5. 2 goes to 5 in the same reaction that 1 went to 4. 2, yeah, going, I don't know, baby boo. 2 goes to 5. It went from +1 to -1. That is definitely called reduction. That means atom 2 became reduced. Which atom became reduced? Atom 2. It went down in oxidation state. Okay? And atom 3 corresponds to what Roman numeral? It's not really Roman. Oh, I have it. Species 2 became species 4, so 3 became 6. 3 became 6. 0 to +2, it went up. What do you call that? Oxidation. That was atom 3. I know it's not much room in there, but there's your answer. In terms of things I need to see on your activity, I need to see this 3 and this 2. I don't need to see any other words. I need these 6 numbers. That's all I need up here. These 2 little Roman numerals and the 6 numbers. And my apologies, I can't read properly anymore, obviously. Thinking oxygen is the same as carbon. Okay.
So the agent is just Lincoln, right?
Oh, I don't like hearing it that way. No, no. I know. Well, you know, you can't. You go back to first principles. You can't have an oxidation without a reduction, right? It just doesn't happen. You got to have both partners in a reaction, something becoming oxidized and something becoming reduced, right? Okay, so a species became oxidized, it must have been the reducing agent was your logic, right? You can have an example where this carbon in a molecule became oxidized and a different carbon in the same molecule became reduced. And now what are you saying? That molecule, here's how I look at it. What does an agent do in life? If you're an agent in the FBI, what do? You do FBI stuff for the agency, right? You do things. You're active. Well, reducing agent has one job, and I just told you what it does. It's an agent of reduction. It causes reduction. So here's how I do the question. I find the reduction, and I say, oh, the only reason that reduction happened is the other molecule made it happen. If that other molecule wasn't there, this guy wouldn't change. So I find the reduction is atom 2 got reduced. Well, species 1 can't be the reducing agent. The other agent caused the reduction. The other species caused it. Species 2 is the reducing agent. And then I find where did the oxidation happen? Point to an atom. It happened. Yeah, I didn't write it down though. It happened in gray, from 3 to 6. Well, this species is the one that got oxidized, right? Must have been the other one that caused it. Species 1. If no species 1, no oxidation of species 2. There you go. Now you're not just memorizing words for the sake of memorizing words. Memorizing concepts gets you through the science better. The agent causes what it says it's supposed to do. Okay. Lots of other videos on this that were a little with a few less mistakes. So look for those. And we will, I'm gonna blame this nasty message here. And